I'll start a recording locally on IFG. So that's in place. So what we looked at were sort of fairly horrible bits of program to look at. And this line, for example, creates a data input stream from an input stream, a very basic input stream. So what will go within these brackets is simply the name of an input stream. And new data output input stream is actually going to create a brand new amalgamated data input stream with a particular input stream. So an example, actual programming example of that is, well, clever clogs is of type data input stream, and it results from creating a new data input stream attached to system.in. And if you remember last week, I actually simply stated that system.in is a well-known Java basic uh, input stream which is actually connected to the keyboard. So, and what a data input stream will allow you to do is to obtain different chunks of data by means of the methods that this class, this particular object, gives you. And that was quite important. So the idea is, just to uh, be very boring and just remind you what we covered last week, is that this is going to be a reader in red, and this is going to be a basic input stream. Basic blue input stream is actually going to offer you very simple methods like read uh, an integer, or possibly read an array of integers, which might not be quite what we wanted. I mean, if we're reading um, a Dickens novel from stored in a particular file, it'd be very nice if we actually had something slightly different, a different range of methods appropriate to our interests. So we can combine the two entities, the data input stream and the basic input stream, simply by writing something of this form. And I do want you to be able to do that and to become happy and familiar by doing that. And if I put something like CK as a new red joined to blue, where red is a data input stream, blue is the simple input, input stream, then if we wanted to execute the methods W1 and W2 found in red, found in this data input stream, all I have to do is to write the name of the object, ck dot, and the name of the method I want to use. So this might be simply um, read, maybe read an array of bytes or something along those lines. And one of the documents I'm putting onto um, Pharos is a summary of some of the methods found in some of the classes. And if you want more details or you want information about other readers or writers or streams, you can very easily find that information from Oracle, and I'll give you details about how to do that as well. So anyway, to summarise, we looked at readers and writers briefly, and we looked at the essential use of the following code, if you remember. Um, it's just this while loop, and it's quite interesting because it represents some program code that's capable of reading data from, say, a file or some other stream, and or maybe a keyboard, or it could be the internet or something along those lines. And I'm going to repeatedly send the data that I've just read in out on an output stream. So you can think of it as almost like a transfer function, getting data in, and each time I get some data in, send it out. It's like a relay station, if you like. And the interesting analogy I told you about was, well, you could use this kind of program construction to copy a file into a new file, or copy a file all the way to an internet client. Sorry about that spelling. Internet client. I mean, maybe an internet client has requested a particular file, and well, the file might be text, or it might be an audio uh, uh, clip, or it might be a video clip, or it might be some other kind of data. Um, and this very easy, if you think about it. It's not that difficult um, to understand. This basic programming construction will do part of the job. Well, I explained it in terms of, well, what the read operation does, and it takes an array, perhaps, of bytes as an argument. Um, and the method read belongs to this, I guess, input stream, or data input stream called fin. And each time I execute it, um, I'm going to uh, assign to n the number of bytes actually successfully read. And providing there are bytes to be read, in other words, an n is greater than -1, I'm going to perform a similar operation to send out the array of bytes out on an output stream. So I want you to come to understand this. And here I'm actually talking about fin, and fin is a file input stream. And as a very short, easy exercise, check out file input stream and document 2 or 3 of the methods that you find there. And it should give you information about what happens if the read operation returns a value -1. It simply means that there's no more data to be read. So you finish reading the file. So I think I asked you to use the Java program called cfile, and it is doing just what I've stated. It's copying a particular file. It copies a particular file to another file, and if the new file doesn't actually exist, it will create it and then copy the file. Did you manage to find a file to copy? I'd like you to do that. And this question brings me to ask you the further question, whether or not you've actually managed to install um, Eclipse. So please let me know if you haven't already managed to install Eclipse, or if you're having any problems using it. But I think I've actually posted a file called cfile.java into Pharos, and what I'd like you to do is just to cut and paste it into Eclipse, and maybe specify the whereabouts of the source file and the whereabouts of where you want the new file to be placed. And the file actually gives you an indication of how to do that. If you look at the file, it's copying what in fact was a very large file on my disk, but it shows you how to do that. The actual file I've given you shows you how to do that. So this week, I'm sorry about the lengthy introduction, but what I'm talking about is something quite important because it will enable us to do some quite interesting things. And remember, if there's any problem and you're coming to understand that, just let me know, and can always set up an additional session, and I can give you some additional examples explaining how to do these things. So this week we're going to look at the theory of TCP. So TCP is the second major protocol that we're going to have a look at. And we're going to look at the basics of that. And the theory part consists in defining what is meant by a connection between two platforms, two internet stations, and we're going to investigate how a TCP connection can give us reliability and how TCP provides us with a method for controlling traffic on the internet. So, for example, if we determine that there is congestion on the internet, then TCP can, to a great extent, cope with and manage that situation. I mean, think about it. I mean, if the motorway is desperately congested and it comes to a halt, what's the point? What's the point of actually starting to travel on it, or in the case of the internet, or what's the point of actually attempting to send data packets over the internet? Um, so it's a way of regulating the traffic on the internet. And an exercise is going to be for you to execute two TCP based programs. And the first is called TCP Echo Client, and the second is TCP Echo Server. And when you get to see that execution, you might think, oh, well, this is a bit boring. I mean, all that happens is that Chris Kinberg can type in a message, and the message is going to be sent to a particular server in New York, and the server in New York is actually going to reply after having processed the data I've sent the server. And the actual processing of data is very, very simple. It's just going to turn text into uppercase text. But it's the principle of being able to do that really matters. I mean, you can change the example. If you want to try changing the example and make it more interesting, you're welcome to do that. For example, maybe I'm going to send a sentence to the server in New York, and what the server is going to do is to translate it into Arabic. Or I'm actually going to send some financial data to a server in New York, and what the server in New York is going to do is to tell me about Bitcoin opportunities. I mean, I didn't know until last night that it's an extremely good time to start investing in cryptocurrency. And I heard about one person who offers to train other people how to invest in cryptocurrency, how to literally double your money. I mean, and they gave me an example of somebody investing £100,000, and within hours it had made £200,000. Well, okay, making money might not be your prime interest in life, or you might frown upon the fact that you can make money without having to work very hard for it, but that's another issue. And the second thing I want you to do is to execute a simple web server running on your machine on port 1234, which allows your web browser to connect to it, and in order to download the message that the web server wants you to display. And if you like, you can actually modify the message because it's very simple, and it's a bit boring, and you might like to just capture it in a screen dump and show me. So that might sound horrendously complicated, but all I'm actually asking you to do is to gain some experience in using Java. So Razan, I've just noticed that you're here, so it's good to, as it were, virtually see you. And of course, I can't see you, but I'm aware of your presence. Good that you're here, and I don't know whether you had managed to have a look at the work that we did last week, but this week's work and last week's work's pretty important in the sense that we're doing probably the most advanced part of the course in these 2 weeks. So it's worth just investing a little bit of time. And once again, if you're having any difficulties in the material, let me know, and I'll make alternative arrangements. Promise you. So don't worry about. Yeah, go ahead. Just say that again. Yes, I'm aware of your. No, not. I'm aware of part of your situation. No. Do you want to tell me privately, or? Okay, well, just send me a quick email sometime. I'm aware of your situation to the extent that you're someone who's joined the course more than halfway through, and that represents a bit of a problem. And I think a couple of other people are in a similar situation. Oh, okay. Okay, well, just let me know, Razan, and I'm happy to talk to you outside class anytime. All right. So take care, Mohammed. Um, no, I haven't received it yet, and I'm not quite sure whether you sent it by email or whether you actually sent it to Michael, because I think you sent your work to Michael last time, didn't you, or something? So just make sure I have got a copy. Okay, I'll have a look for it and I'll let you know a bit later on this afternoon. Thank you for doing that. And I mean that we're making progress. Okay, so as I said, we're at the point in the course where we're doing some fairly tricky stuff, and it it should be very very new to you. But um, I'm asking you to take things a little bit on in good faith and just familiarize yourself with the use of Eclipse and using Eclipse to actually cut and paste a program. And then we're going to actually have a look at the programs themselves and come to understand what they're doing and how they're doing what they're doing, as it were. I mean, we're looking at it from a computer science and programming point of view, and we're doing things in stages. And I mean, my strategy is, first of all, I tell you a little bit about the theory of IP, for example, and then we look at the applications of IP. I mean, we haven't done very much of that, but I think by now we should have an understanding of IP and the way in which the IP protocol is capable of carrying data. In particular, it can carry uh, TCP uh, datagrams, or what are called TCP segments, piggyback. I mean, you can use IP as the vehicle for transporting data. And one other protocol we're likely to have a look at is UDP. And again, UDP is is going to be encapsulated in IP. So the reason I said when I started talking about the internet was that IP is the workhorse of the internet, is that it does a lot of work in transporting or transferring or communicating packets. So this week we're going to have a look at the theory of TCP. We're going to have to find out what TCP looks like and how it can be used and some of its very important properties. I mean, the revolution in internet communications really is based on the features that TCP offers. And armed with a language like Java, I mean, you and I can both easily program uh, internet applications. I mean, I can develop an application and I can use the application to provide a service to you wherever you are in the world. And the reason I first became interested in TCP was that it was being used for remote surgery from doctors in London to patients in Canada. I mean, TCP was using to control some very sophisticated medical equipment in Alberta, in Canada. And, the operation performed was successful. And it was all done over the internet. Very reliable protocol. Data, it's guaranteed to send the control signals it needed to send to the equipment, and it was presenting the team in London with very clear visuals as to what was happening. I don't know, is it 5,000 miles away or whatever? So, as I said, as a sort of very, very simple illustration of this, I'm asking you to use the programs I'm giving you, uh, and you will, after today's session, you'll recognize a lot of the program content of the client and the server, and you'll understand how it's doing things. So I want you to focus on that. And the second example is just simply executing a simple web server running on your machine on a particular port. So hopefully the idea of ports are beginning to make a bit of sense. In virtue of the fact that I think we've mentioned the idea of a socket, and a socket really can be thought of simply as a pair of things. It's going to be, you can think of a socket as a class or an object which contains a port number and a 32-bit IP Internet Protocol address, together with some other methods for allowing you to determine input and output streams on which you can communicate with a far distant machine, So we'll revisit that just to make sure we understand that. And I might even sort of try using Pharos to give you a live demonstration of what I'm talking about here. But usually when I try to do live experiments using Pharos, it crashes. So, but we'll do that in good time. So and a bit later on. So let me see if I've got any more. So I think that's all I've got to show you from that point of view. So I'm going to turn to TCP to begin with, and then we'll look at some programming aspects of TCP. So okay, I'm starting to upload this document, and the system is beginning to convert the file, and the system's a bit of a slow one at times. and I'll keep you updated on the rate at which it's processing the documents. Okay, it's doing it actually very quickly. So, and it's quite a large document for you to refer to. I'm not expecting you to read the whole of it by any means at all. So this is the tricky bit. It's been processed. It's been uploaded. I'm expecting um, to see the document appear any moment. Okay, here we are. So I think I'm right in saying that I've got the date wrong. It's not the 19th of April. Trying to be a bit futuristic here. It's the it's the 14th of May. So I apologise for that. No, I'm not. It's looking backwards. I'm getting very confused because it should have actually read the 14th of May, today's date. Um, so what we're going to do is to first of all identify and understand the services offered by this software package running on your laptop and running on any remote laptop with which you're going to communicate. And secondly, I want you to come to understand TCP's flow and error control and congestion control facilities. Right? So TCP can control the flow of data it sends to you, and it can manage errors that occur. And what I'm thinking about is, and what I count as an error is that Raghead, if I send you uh, some data and it doesn't arrive, that is an error. Why? It's because TCP has got to be seen to be reliable. I want every tiny bit of data I send to you for you to receive that data. And I've mentioned congestion control a bit, so we're going to have a quick look, if we've got time, to see how the congestion control facility works. And that just means what are the ways in which TCP can detect the presence of congestion out there in the network, and what should it do if it actually detects congestion. And so fourthly, and I think this is pretty significant, I want you to be able to think about the critical phase in setting up a connection between two machines. What's involved in making a connection, a logical connection between laptop A in Russia and laptop B in New York? What's involved in that? And we're going to discover that it's very closely related. The mechanism for establishing connection is very closely connection to what we earlier described as synchronization last term. You remember all the work that we did on synchronization? It's like if two independent systems want to talk to one another, they've somehow got to prepare for what the French would call a rendezvous. They've got to establish some form of handshake. Machine A has got to tell Machine B that it wants to talk to Machine B. And Machine B, similarly, needs some kind of mechanism for telling A that it's listening and it's seen Machine A's request and it's ready to go. And from that point onwards, the two systems could communicate. And I'm talking about something very, very, very general here. Uh, and the kind of generality begins with two people wanting to talk to one another and they're being able to synchronize and observe some kind of protocol for talking to one another, all the way to two microscopic electronic systems that want to communicate data with one another. And the simple fact of the matter is that one system might not uh, see the other system's attempts to communicate, so they need to perform some kind of handshake. So hopefully, um, most of you who've, by now have got some idea of handshaking. Well, at a different, completely different level of operation, we're looking at network devices. And they, like human beings and like tiny digital systems, need to communicate with one another, and they need to what I call rendezvous appropriately. They need to perform some kind of handshake. And in the case of TCP, it's called um, a three-way handshake. A three-way handshake, and we're going to look at that in some sort of detail. We'll see how that's actually done. Next lecture, well, I'm not even sure there's going to be a next lecture on TCP, but we might have a look at timers, the use of timers, and might, uh, interesting, it's quite an interesting topic, the use of TCP options. And, but I mean, you might think, well, what on earth are you talking about, timers? Well, it can be very simply explained at one level, and it's that if I send Raghad communication and I don't get an acknowledgement back within 300 milliseconds, I might decide to send Raghad the same data again. I mean, I'm assuming that it's somehow got lost, or it's been too late in arriving for Raghad to make any kind of use of it at the time. But we'll investigate all that. So we've looked at IP, and Razan IP doesn't have flow control, and I mentioned internet control. I think its messaging protocol might be of some help here, in the sense that if a router discards an IP packet, mainly because it's very busy, it will send uh, a message to the effect that I've just dropped a packet that you've sent me, and it might be of some help, but it's probably not very helpful. We haven't looked at UDP in this course so far. It doesn't have any flow control, but TCP offers flow control and error control. Okay, so let me just make sure I haven't. It offers flow control, which is going to be quite important. So, in the grand scheme of things, what I'm showing you here is the what's called the protocol stack. And if you remember, at the very low levels, you've got the hardware uh, systems capable of sending out packets of data in various forms. And at a slightly higher level, you've got the IP protocol, into which the data is going to be put into an IP packet, and the IP packet is going to call on the hardware level layers to do the sending of the packet. And similarly, TCP, which is one of, I think, several well-known protocols, including UDP, TCP is going to use IP, the IP packet, uh, to transport it, and this packet's going to call on the hardware services to do the actual transmission of all this data. And at the highest level, you've got very well known applications called domain name server, um, file transport protocol. If you want to request a file, you can use this protocol, and it's reliable. It's going to use TCP. And there's mail transport protocol, and all sorts, lots and lots and lots of different applications at the applications layer. And things like Zoom or BBB or Moodle might be somewhere here, and they're going to call on. I mean, they might even be here, and they're going to call on the services of TCP or UDP and so on. So, so maybe I've got Zoom here, and I'm going to send an audio packet to you 5,000 miles away to a particular IP address, a particular port number on which you're listening. You'll be listening on that port number, and your Zoom application will be talking to my Zoom application via the two protocol stacks. The first on the sender side, and the other on the receiver side. Okay, so what are the services offered by TCP? Well, let me just run through a list very quickly to begin with. They allow an application, I'm saying processed, but I mean an application that you've written or you've developed or you're using to talk to a remote process or a remote application. So it allows communication between different processes. And one way in which they do that, the way in which they do that is principally through the use of port numbers. I mean, if I send Mohammed a communication address to his IP address on port 999, then when Mohammed's machine receives that, it's going to take the TCP packet that's just arrived and send the contents, the key contents of that packet, to the process which is listening on port 999. The port number helps to identify amongst possibly thousands of different processes or applications running on Mohammed's machine. So the key thing is that it facilitates TCP facilitates process-to-process communications. And secondly, it's going to allow what's called stream delivery service. Streams can deliver a stream. And I'm going to explain what I understand by stream. I understand by stream a connection. In a connection by means of which I can repeatedly send Razan or Mohammed data, and it's as though it's a dedicated channel of communications. It's as though it's a dedicated channel of communications. But I'm going to talk about that a little bit. TCP can offer duplex communications. What do I mean by duplex? Technical phrase meaning bidirectional communications, full duplex communications. I mean, it could be something like voice over. It could be an internet telephone. It could be communications in a very obvious sense of audio, two-way audio communications. or it could be something like a web server which not only allows clients to communicate with the server, but it allows the server to communicate with the clients at the same time that the client's communicating with the server. And okay, so this is very closely related to stream delivery service. It's connection-oriented service. Connection-oriented service. And um, as far as IP is concerned, that doesn't provide a connection-oriented service. Why? Well, in the sense that uh, IP simply has the responsibility of sending chunks of data to a destination. And it's dumb in the sense that it doesn't know what it's just sent, and it couldn't care less as to whether the data that it's just sent uh, arrives at the destination. It couldn't care less. All its job is to simply send out data, as though the data was independent of each chunk that's been sent. And critically, and fifthly, TCP provides reliability. So, I've just sent a facsimile of a check worth £500,000 to my agent in South America, and I can not worry. I don't have to worry about whether or not that check is going to be sent to my agent. It will get there, no matter what. Okay, so there's it's a range of different concepts, and you might think, well, the duplex communication's a bit trivial, but in fact it's not, because I'm talking about um, inbound and outbound parallel communications. I mean, I might want to. An example of what I'm talking about is that maybe um, talking. Uh, um, I'm sending the contents of a show to America, where there's people talking in America and talking to me, and I'm talking to them. So it's interactive. But I might want to have a channel that enables me to pull the plug in, or to stop communications at any second, and that requires a communication in one direction that's quite independent of the main communication. But I mean, that's a bit vague, and I'm likely to return to that. Okay, so can I just say one thing? TCP has what's called well-known ports. So, for example, port 80 is used by web servers, and it's used to communicate using HTTP, hypertext transport, which goes on top of. I'm using TCP to send commands to a server, such as get me your default web page, or and so on and so on. Or maybe I'm going to send using HTTP, which is running using TCP. It might send information about what I'm sending you. I'm maybe sending you ASCII code, or maybe I'm sending you numerical data, or whatever. And I've got a lot of ways of assisting communication to a web server. Telnet you don't hear very much about, but it uses a default well-known port 29. I mean, Telnet actually gives you access to a screen running on your system. I mean, it's a pop-up screen that I can use to maybe execute programs on your machine. FTP, two ports, 20 and 21. Use 20 to receive and ask for data, and 21 I can use port 20. Um, 21 I can use to specify the, the data I want to be sent, and port 20 is the port number through which data is going to be sent to me and received on my side. And there are other things, like if you're using Unix machine, and if I communicate with port 11, which again is a well-known port, it can tell me who's using your Unix machine. Give me a list of all the users. And port 7 is an echo. Uh, what's going to run on port 7 is an echo server, and it simply echoes any datagram that's been received. Okay, so that's quite interesting. I mean, I can actually test. Um, I can actually um, okay, Mohammed, I've just received your email on my on my telephone, so I'll respond to that a bit later on. Okay, so here's a sort of might seem a random list of well-known ports, but of course there's going to be a possibility of 65,000 different ports supported by TCP. 65,000 different ports. Here are a few of what are called the well-known ports, and one other port that's extremely interesting to my mind is called. I mean, I can't honestly remember what the port number is, but it supports what's called AG. No, I'm trying ATP, Agent Transport Protocol. And that's particularly interesting because if your machine is running an application called ATP, then I can send, using that well-known port, a Java program of of considerable complexity that might decide to completely take over your machine and become my machine. In other words, the potential is for me to take complete control, for good or for bad, on a remote machine. So something that you might want to investigate a bit later on. It's interesting and it's powerful and it's potentially quite dangerous. So I'm not going to tell you about Unix. This course is not about Unix. The well-known ports are all stored in a file called services in the subdirectory called etc. And each line in the file gives the name of the server and the well-known port number. And you can perform various operations on services. For example, if you want to find out all the relevant TCP ports, you can do that by using a Unix command called grep, but I'm not going into that at the moment. So this is the situation, and I want you to look at it, and it's not hard. But here am I'm the sender, I'm using TCP, and I'm sending you what literally is a stream of bytes. In other words, it's a sequence of connected bytes as part of one communication. All right, a stream of bytes. I don't want you to confuse stream here in the sense of a Java stream, which is just the end point of a communication. I'm talking about a moving sequence of bytes being transported from a sender to a receiver. And the point of showing you this is that the stream of byte is a virtual connection. It's not a real connection, it's a virtual connection. And the question is going to be, well, how do you set up this virtual connection? How do you do it? We'll return to that. Right. TCP, unlike some other protocols like IP, is stream oriented. UDP sends data in discrete, independent chunks. TCP can send data as a single stream of around about 30 gigabytes if it wants to. Um, Sender and receiver, other things being equal, cannot read or write data at the same time, and you need some kind of buffering to do that. You know, if you send me data whilst I'm sending you data, I need to store what you sent to me in a buffer in some temporary storage. And there are two buffers, two main buffers, one on the sender side, one on the receiver side. And I'm looking at how do you actually transfer a stream of bytes, a stream of data to a receiver. Well, the sender's buffer has three logical sorts of chamber, and you can think of these different chambers, these different cells, as having a colour: white, grey, and some colour. I mean, I don't know, but some pink. So the white indicates empty, and that is a cell or a chamber waiting to be filled by a data producer. So I'm going to put data into that when I've got it to give to you, or I want it sending to the sender. And I've got some grey cells which represent all the items of data I've sent but have not yet been acknowledged. And the data in coloured cells are those items that are ready to be sent but I haven't actually sent. In other words, if other conditions are met, for example, there's no congestion present out there on the internet. So let me graphically show you this. Oh, I'll show you in a moment. So the receiver's buffer is simpler than the sender's buffer. You've just got two areas, two types of cell. You've got white, which are to be filled in with new data as it arrives, and coloured cells, which are received bytes that could be read whenever the receiver is ready to. You know, the receiver might be busy. It might be busy gobbling up all the data it's received up to now, and there's been a lot of data coming in. And the purpose of buffers, so I'm going to show you a diagram to make all this clear in a moment. The purpose of buffers is simply to resolve, okay, technical phrase coming up, the bandwidth differences between receiver and sender. Just as a car's shock absorbers will dampen down the peak, I don't know, the peak, let me say, movements of the tyre travelling across a rocky road, dampen down the peak data rates. So buffers are going to be used as shock absorbers. In other words, if you suddenly, if Razan, if you suddenly decide to send me an awful lot of information in a small space of time, I need some way of temporarily storing what you've sent me, because perhaps I'm not actually listening to you at the moment. I need to store it so that the message, your vital data, does actually get to me eventually. I need to buffer it, what's called buffer it. Oh, here we go. I haven't got to the diagrams yet. IP provides services to TCP. Well, we know that. And it sends data organized by TCP into a connected sequence or segment of discrete packets. A connected sequence of discrete packets. And TCP adds headers to each segment of data that it's sending for control purposes. And these segments, these chunks of data, including a header, are going to be encapsulated into an IP packet or datagram. Means the same. So this is a bit long-winded, I'm afraid. So segments can be received. Okay, so I'm sending, the scenario is this. I'm using TCP to send and receive data. I'm sending it in the current example. Sorry, I'm going to receive some TCP data. I'm the receiver, I'm receiving some data. I might well receive data that's out of order. I might, some segments might be lost. Some segments might have been corrupted and have been resent. Well, none of that represents a problem to TCP. So if I get 6 packets or segments out of order, in other words, the order that I receive them are different from the order in which they've been sent, I can reorder them. I've got all the control mechanisms to do that. If a segment has been lost on its trip to me, then I will know about it and I can actually request that it be resent. I can do something about a lost packet. And you might say, well, what? Well, that'll all fit in to the TCP story. I can check to make sure that a TCP packet hasn't been corrupted. And if a packet has been lost or it has been corrupted, I can request for it to be resent. So TCP is going to handle all this, and it's important. I mean, if Razan actually talks to me, as she did a few minutes ago, I can actually say, I didn't. Can you repeat that? Because I didn't hear you clearly. And it's true, I didn't actually hear Razan clearly the first time. I heard her clearly the second time. She retransmitted the audio data again at my request. So TCP handles all that and handles it transparently to the receiving process at the destination. So TCP is doing all this work, and what the receiving process, the receiving application, the receiving application won't have to do anything, any work. It doesn't have to resequence out of sequence data. It doesn't have to request lost packets. It's all done for the application. Right, segments are of variable length. TCP offers full duplex service. And as I said earlier, there can be simultaneous transmission from the sender to receiver and vice versa. Okay, so I think I'm just going on and on and on, but at least you've got a physical record of what I'm talking about, and you can, in your own time, you can go through all this and check to make sure it's making a bit of sense. Okay, So TCP offers connection-oriented service, a connection-oriented service. So when A wishes to send and receive data to and from B, the two TCPs, one at the receive end, one at the sending side, will establish a connection and data will be exchanged. And then after the communication has taken place, the connection will be closed. And the connection's virtual, which I haven't explained yet, and it's not physical. Okay, the connection I'm going to establish with Ragad is not a physical connection; it's a virtual connection. So we need to sort of find out a little bit about that. So here's a little diagram, which is my best attempt to explain the nature of a virtual connection. It's not a real connection; it's a virtual connection. And what I'm showing you here, principally, as the sender A and the receiver B. B is here. And what this blue line indicates is the virtual connection. And what do I mean by that? Well, I can explain it actually very simply by saying a couple of things. These green dots represent routers lying in between A and B. So these are real routers, and the arcs in varying colours represent physical uh, connections between routers. For example, this connection here might be a microwave connection. This connection might be an Ethernet connection. This connection, the connection between these two routers might be a Wi-Fi connection. The connection between this router and this router might be a wide area network connection, and so on. So there's all these routers that separate B from A. And I'm going to, well, maybe A is, well, I'm going to send a communication whose destination is B. And the problem for router A is, what's the best possible, I mean, this is a possibility. What's the what's the best possible route from A to the next router? The next router. Should I go here or should I go here? Given the fact that I actually eventually want to get to B. Well, router A is going to make a decision. Maybe it says I'm going to send it to this router here. Then the problem is in this router's court, because it can send it either here or here or here. And maybe this second router decides to send my packet to this router here. Given that this router knows that my destination, the destination of the packet is actually B. I mean, the routers have maintained routing tables, and they're updated by means of, well, okay, this was a route, but this router here knows that this router is out of service. So it diverts all its traffic to this router or that router. I'm assuming that this router, for whatever reason, local reason it has, is going to send my packet to this router. And this router doesn't have any choice. It's got to send it on to this router. And maybe this router is going to send it to this router, and then it's just one hop away and we reach the destination. So think about it. I've got lots of different routes, physical, real routes through the internet, through this network of routers. And so I'd state that again, there are lots of real physical routes through the network. But once um, I get, I establish a particular route. I mean, maybe watch my cursor, it's going to be this. Once I've established a connection, uh, all that matters is that the data actually follows that particular route. It's successful. But then 5 minutes later, something happens. I mean, maybe the network in this area becomes very busy. Therefore, this router is going to say, "Okay, I'm going to send Kinberg's data to this router. I'm going to try and bypass congestion." So you can see, for successive TCP segments, different physical routes might be chosen. But all that matters is that starting from A, all my data gets to B. And I can conceptualize what's happening as A following a virtual route to B. It doesn't really matter what the physical route is. As long as I've got a physical capability of transporting data to B, I've got this connection. And I couldn't care less whether the real physical connection changes from minute to minute. I couldn't care less. Okay, so hopefully that's reasonable. Okay, TCP's reliability depends on the use of acknowledgements. That that guarantees reliability, amongst other things. Okay, so we're back to where I want to be. These are the two buffers, and I need to explain this to you. So here I've got, remember I spoke about three different coloured of cells, and you can think of it as I suppose a wheel of memory, and it's turning in a clockwise fashion. It's a buffer. It's being used to temporarily store data. Which data? Well, the data created by the sender. The sender's actually going to put some data in to this moving wheel at the next available empty cell. So this is now about to become pink, and the buffer moves, and at this point I'm going to, this is this chunk of data here, this cell full of data created by the sender is going to be sent out on my virtual channel, my virtual stream, my virtual connection. And the sender could produce quite a lot of data quite quickly because there's enough space in the buffer to temporarily store it. But the way in which all this operates is that I put data in to an empty slot, and I send the next byte to be sent, which is this one here, because I'm going to keep a note of which byte I've just sent. And then the next byte to be sent will be this one here, can send that. And these bytes are is the data that I've actually sent but have not yet received an acknowledgement. So I'm going to keep storing those. I'm not going to lose those. And in fact, what's going to happen is that if I get an acknowledgement for this particular chunk of data, I can forget about it. I can just empty it, make it white. If I get three acknowledgements for these chunks of data, I can make these white. And eventually these buffers will turn full circle and receive more data to be sent. Okay, so that to me is fairly easy to understand. And the key idea is that it is a buffer. I'm storing data in preparation for sending it out. I can control the data I send. I mean, if you think about it, if for some reason, um, if for some reason uh, I was told that there's no point in sending out data because it's not going to get there quickly, I could just stop the rate at which I'm going to send data. And meanwhile, the sender is actually going to continue filling the buffer in data that it has created. But eventually, because it's a finite buffer, it's going to become full, in which case the sending process will actually have to stop. So there is some kind of mechanism here for uh, dampening down uh, peak data rates. You know. Anyway, think about the receiving process. Well, it's much simpler. I've got some empty cells here, which I can fill up in turn, and these pink items, these coloured items, represent data I've received, but which have not yet been consumed by the receiver. So again, this is behaving as a buffer in the sense that I'm going to use this temporary storage to fill it up with data which I cannot yet send to the receiver. The receiver process might be very slow. It can be 1 byte a second. But what actually comes in is 60 bytes per second. So I'm safely buffering the data I've received. I'm dampening down the peak rate of receiving data. And this is what I'm talking about when I talk about data bandwidth mismatch. The sender might be much faster in producing data than the receiver is at consuming data, or vice versa. I mean, the receiver could gobble all the data it's got within 10 microseconds, but it's taken the sender a whole day to produce the data. I mean, maybe the receiver process operates, I don't know, once a day, but when it's active, it's going to gobble data up very, very, very rapidly indeed. So that's the receiving process. In this case, is going to be faster than the sending process. But the sender process could generate gigabytes of data. And here is poor Chris Kinberg, with a lot of data to process. And he can only process at 1 megabyte per second or something along those lines. So I don't know why I'm showing you this, but really, I mean, the sender is actually going to package the data it's got that's being held in the buffer in a sequence of segments. I mean, maybe this turquoise chunk was actually goes into segment 1. It's been sent over the internet, and this chunk of data, this pink bit of data, is going to form the content of the nth segment. And it's just a sequence of bytes which has been preceded by a segment header, which we haven't looked at yet. Okay, so this gives you some insight into TCP software in terms of how it sends data and how it receives data, and there's a fair amount of detail to look at. So to provide the services I've just mentioned, um, and that's the features are flow control, error control, congestion control, and a numbering system, because I want to be able to number segments. I want to be able to number segments so I can get some kind of handle on their control. Okay, so a segment header. So I'm looking at a TCP packet or segment, and I'm going to look at the header first of all. The header contains two important fields, a sequence number and an acknowledgement number. All right, a sequence number and an acknowledgement number. There's no segment number as such. All right, a sequence number is going to be a random number, and an acknowledgement number is going to represent the sender. Oh, well, we'll look at that in detail in a moment. I'm just being distracted by something else. So these fields refer to byte numbers. TCP labels all bytes transmitted. When TCP receives bytes, it stores them in the buffer and numbers them. All right, so that's important. So the bytes of data transferred in each connection are numbered by TCP. The numbering starts with a randomly generated number. All right, so supposing a TCP connection is transferring a file of 5,000 bytes. First byte is going to be numbered 10,001. What are the sequence numbers for each segment if data is sent in 5 segments, each carrying 1,000 bytes? Well, if the first byte is labelled 10,001 and it's going to what's it, 5,000 bytes? So segment 1 is going to have a range from 10,001 to 11,000, so I don't know how that's worked out. Perhaps you can tell me. What are the sequence numbers for each segment if the data is sent in 5 segments, each containing 1,000? Okay, well, here's the first segment. The first random the first byte is randomly assigned the number 10,001. Therefore, the last byte to be sent is going to be labelled 11,000. And in the second segment, you're going to label the first byte to be transmitted as 11,001 and the last byte 12,000 and so on. Well, that's easy enough. Right. TCP segments and sequence numbers. Right. If a segment carries data and control information, it uses a sequence number. If it carries no data, there's no sequence number. But there's no sequence number used. But some segments carrying control information need a sequence number to allow an ACK from the receiver, which is used for establishing connections. These consume one sequence number, but no data is carried. That might sound very, very complicated. And X plus 1 is going to be the sequence number for such a control segment. So, for example, if I simply want to send an ACK, I'm going to increment the sequence number by 1. So, the value in the sequence number field of a segment defines the number of the first data byte contained in that sequence. Okay, we've seen that. The value of the acknowledgement field in a segment defines the number of the next byte a party expects to receive. Right, the value of the acknowledgement field in a segment defines the number of the next byte a communication partner expects to receive, and the acknowledgement number is cumulative. Alright, so let me see if I can show you. I'm jumping ahead a few slides because I think that's just giving you too much detail to absorb at the moment. Right. This is the structure of the header of a TCP header, and notice first of all that unlike IP, there's no destination address, 32-bit destination address. There's no 32-bit sender address, but what there is, a source port address. This is the port from which this segment was sent, and there's a destination port address that's 16 bits long. And I guess if it's 16 bits long, I mean, you can do this calculation. There are 2 raised to the power of 16 potential port addresses, 65,000 odd. So there's quite a huge number of possible port addresses. And similarly with the, I can choose a random port address from 65,000 odd different port numbers to send a segment to you. Right. Then there's a 32-bit segment number, and the initial segment number of a stream of segments is random. Then it contains what's called an acknowledgement number, which is 32 bits long. And as I said a moment ago, an acknowledgement number is telling your communication partner which segment you are next expecting. So, for example, if this acknowledgement number is X, it's actually saying I'm expecting to receive the next packet, the next segment I'm expecting to receive from you is a packet with sequence number of X plus 1. X plus 1. And have a look at the next 5 bytes. This is each of these layers is 5 bytes long, and I've got a header length 4 bits, reserve bit, and then several bit fields, and these are quite interesting. This is called an urgent pointer, which I'm not going to talk to you about. This bit, if it's 1, means that the acknowledgement number specified here is valid, and I, as a packet, as a segment, behaving as an acknowledgement. I mean, just to repeat what I mean, this is important. If I've got an acknowledgement of X and the ACK bit is 1, it's actually saying I've received all the packets with sequence number up to and including X, and the next packet I'm expecting is a packet with sequence number of X plus 1. Okay, that's important, and if you spend time just understanding what I've just said and relating it to a little bit more material that I'm going to tell you about, you will have cracked something at the heart of understanding TCP and its operation. And I'm just going to talk a little bit more about um, these three fields. I'm not going to talk about the push field, but I want to talk about the RST bit and the synchronization bit and the finish bit. If I send you a packet with the reset field 1, I'm telling you just to I'm not talking to you anymore. I've had enough of you. I'm doing a reset. If this bit is set to 1, it means I'm asking for you to establish a connection with me. It's a synchronization bit. If I'm the client and I send this to you, I'm expecting you to respond to my request for some kind of synchronization with you. And I'll tell you what's involved in that in a moment or two. And this is the finish bit, and if this is set, I'm asking you to end. No, I'm telling you that I'm not going to talk to you, but you can talk to me. I'm finishing my connection. This segment in which I occur represents the last item of data that I send to you. So this field, 16 bits long, is called the window size field. And this is interesting and important because I can actually specify the size of buffer that I'm expecting you to have. No, I think you've got that the wrong way around. I'm sending you the window size, and I'm actually telling you what my buffer size is. So it could be 1,000,000. And what that means to the receiver of this packet is that you could send me 1,000,000 bytes if you want to, because I've got a buffer that size. Okay, so it's called the receive window. It's called the receive window field here. So lots of different fields. I haven't mentioned this. I haven't mentioned reserved. Haven't mentioned the checksum. Haven't mentioned options. You can have up to 40 bytes of these. I might say a word or two about options later on. So, little reminder of what I've just been telling you about. So I've looked at syn, fin. I've actually looked at reset, but that's not important. The ACK field, if this is a 1, it means that the acknowledgement number I'm carrying is valid, and just take note of it. So okay, just a bit more detail there, and not going to talk about pseudo headers. Not really interested in checksums, and just to, I suppose, the current take-home fact is I might have an Ethernet frame into which I've put an IP header, so I'm using IP to transport this packet of data, which turns out to be a TCP segment, and a TCP segment consists of a TCP header. The important things being is that it contains the port numbers to which a TCP application wants to talk to on the remote internet machine, plus some maybe audio or text or other kind of data. Okay, so I'm coming to a subtopic which is incredibly important, and it's how a connection's established, how data is transferred, and how you terminate a connection that you've created. Okay, so once again, TCP is connection oriented. The main feature of TCP communication is that TCP establishes a virtual connection between sender and receiver. So all segments belonging to a message are then sent over this virtual path. Right, connection-oriented transmission requires three phases. So before you can use a connection, you've got to create it, and you do that in three phases. So a server or a receiver, perhaps, must be ready, and it's got to be listening on a particular port. I mean, I can't, the sender, can't create an internet TCP connection on a particular port unless you're listening on that port. I need somebody to talk to. It's as simple as that. Right, what I'm doing here, I'm terminating the BBB recording, because apparently it can't handle recordings of more than an hour. So the session's not being recorded at the moment. Right, fine. And the client then responds to a request to open a connection, to create a connection. And so the client sends a request. It does what's called an active open of a connection. It sends a request to a server to establish a connection. And the server, in response, is going to send it's going to send the sender an acknowledgement. So can we just have a look at the details of some of this? And this must look horrendous, but it does actually have some explanatory power, and it does clarify things quite a lot, and it gives you a fair amount of detail. So let me start by saying that these vertical lines are called timelines, and it represents, well, it's like a vertical time axis starting at the top and going downwards. Right. So I've got the client here and the server here, and the server, I'm assuming, is listening on a particular port, and the client is actually going to send this TP packet to the port that the server is listening to. Right. So let's just have a look at the segment that's being sent. All right. I've got a random initial sequence number, 8000. So remember, the header contains an identification number. Here it is, 8000. It's random, quite random and arbitrary. Right, ISN, initial sequence number. And one of the bits that I've been talking about is set to 1. And it's the S bit, it's the SYN bit. So all I'm doing here, this packet isn't carrying any data. It's just making a request for the server to respond to my request for a connection. So no data's being sent here. Look, no data's being sent here. So the key things is that the header contains a sequence number and the SYN bit set to 1, indicating that I'm requesting a connection for synchronization. So it arrives, and the server's listening on the given port. Maybe it's port 80, I don't know, or 999, or 20,026. Doesn't really matter. The server is going to respond with an acknowledgement. I'm telling the client, yeah, I've received your packet. How do I do that? I'm sending an acknowledgement number of 8001, and this is the sequence number of the packet sent, the segment sent plus 1. So it's 8000 plus 1, 8001. I'm acknowledging having received everything up to segments including 8000, and I'm actually telling the client that the next packet I expect is going to have a sequence number of 8001. So the acknowledgement bit is 1. That means that this acknowledgement number is valid. Make a note of it. It's valid. And I'm telling the client that I want to synchronize with you too. Look, that's a request for synchronization. Here's a mutual request for synchronization. So, in fact, what this segment represents is both a request for synchronization, a request for establishing a connection, and telling the client that I've received the packet you've just sent. And the thing I want you to note here is quite interesting. The receive window is set to 5000, and that means, look, I'm the server and I've set up a buffer of 5000 bytes. You, the client, can send me as much as 5000 bytes. Don't, whatever you do, send me any more, because my buffer won't hold it. And of course, let's supposing that the client suddenly decided to send 5000 bytes very quickly, and the server's buffer is actually filled up instantly. Well, the server could actually acknowledge that data, but set the receive window to 0. It means, look, I've got nothing left in my buffer. Don't, whatever you do, send me any more data. So you can see that there's some kind of control mechanism taking place here. Right. So when the client receives this packet, I can acknowledge it by saying, I've received packet 15,000. The next packet I'm expecting from you is going to have sequence number 15,001. And I'm telling you, this is all part of setting up the connection. I'm telling you that I've got a buffer, the client has got a buffer of 10,000 bytes, right? So we're sort of negotiating the terms for communication. So since this packet is acting as an acknowledgement, I have to set the acknowledgement bit to be 1. So all that means is that this acknowledgement number is valid. And the mystery about this is that this was a sent packet, a synchronization packet with sequence number 8000. I'm now sending an acknowledgement packet, but the sequence number doesn't change. Because why? Well, let me tell it you straight. It's a control segment which doesn't control any data. So I don't have to increase it. Sequence number is only increased when I'm sending more data. It still stays the same here. So see where my cursor is. From this point onwards, I have got synchronization with the server, and I can start communicating. And the reason I can start communicating is that the server knows what sequence number I'm using, so it's capable of acknowledging data that I send in. I know from what the server's told me how much or how little data to send him or her, and vice versa. I've actually told the server what my uh, buffering capabilities are, and from this point onwards we can communicate. And this establishment of connection is called a three-way handshake. And this is what I want you to remember forever. Alright? Three-way handshake. First of all, I send a packet asking for a connection. And I guess it's going to be seen because the server's actually going to, in turn, send me a request for synchronization. And it's going to acknowledge having received my request. I mean, what happens is if I actually send the server a connection, but I don't get the acknowledgement, what I probably will do is to send out this packet again and again until the server actually sees it. On the other hand, if the server's not listening, definitely not listening, an error will be created because I can't actually send a packet in TCP to a system that's not listening on a particular port. I'm assuming the server is listening on a particular port, say 99. And therefore, if I don't receive this acknowledgement, I can only assume, within a fixed amount of time, I can only assume that this acknowledgement packet has got lost. Alright, and then as a result, I'm going to resend the original packet. But I'll leave you to think about that anyway. So there's just a couple of notes about whether a packet, if a packet is playing the parts of an acknowledgement, if it doesn't carry data, doesn't consume a sequence number. The sequence numbers don't change. If it did contain data, an acknowledgement packet would tell you what the next packet is expected. So so from that point onwards, I can start sending the server data. Here I go, look, it's my sequence number 8001. I've sending you an acknowledgement for the packet that you sent me, and I'm sending you a chunk of data. I'm sending you 1,000 bytes of data. And in fact, I can send you another chunk of data. This sequence number is now sequence 9001. I've updated it. I've just sent you 1,000 bytes of data. So I'm going to increment the sequence number by 1,000. Get 9001. But I'm still sending you the acknowledgement of the fact that I've received a packet from you with sequence number 15,000. And then eventually the server, having received 2,000 chunks of data, I'm going to send the client some data.
and I'm acknowledging the packet with sequence number 10,001. 10,001. Okay, so I've received 10,000 bytes. I'm acknowledging receipt of uh, the next segment I expect from you, I'm waiting for, has a sequence number of 1001. Because this packet has sequence number 9,000. I've sent you 1,000 bytes. Right, I'm sending you 2,000 bytes here, and I'm acknowledging receipt of this packet by I'm telling you that the next packet I'm expecting is 17,001. That's an acknowledgement, and I'm adjusting my receive window here. So this is what's happening here is normal data transfer, and I mentioned the fact that accumulative, sorry, what am I talking about? Acknowledgement numbers are cumulative. So if you sent me 10 packets uh, with 20,000 bytes in total, I can simply send you a simple single segment acknowledgement of all those. So because the acknowledgement number will represent the next byte I'm expecting from you. Okay, so nothing. And I'm not expecting detailed understanding of what follows here, apart from you should know how connection termination takes place using our three-way handshaking. And the way, if the client wants to terminate the connection in this direction, then all it needs to do is to send the fin bit sent to 1, and the server will actually close the connection in that direction by acknowledging, saying I'm expecting the next packet to be x plus 1. Well, this packet had sequence number x, and it too is now, the server actually wants to both acknowledge receipt of this packet, acknowledge receipt of the finish segment, request to finish segment, and it wants to send you, the client, a finish request, and so it's acknowledging this packet x plus 1, and this has a sequence y, and the client, when it receives it, is going to acknowledge receipt of this packet, which has sequence y, by putting the a bit to 1 and acknowledging y plus 1. So it gives you an idea of it's actually a lot of detail here, but it gives you something important. And this is, I'm just talking now at the moment about sort of generalities here. A client can actually half close the connection. In other words, it can close the communication direction in that direction, but leave it open in that direction. So from this point onwards, the server can continue sending the client data, and we'll send the server uh, acknowledgements, and then eventually the server will actually decide to finish. I mean, this green area represents unsent data from the server, which is it wants to send the client, and are not really okay. This is something I want to show you. I mean, hopefully by now we can appreciate the idea that software can be in a number of different states. For example, or systems can be in a number of states. We've had a look at state machines. Um, for example, a, a thread can be in a number of different states. A thread can be running. It might be ready but not running. A thread or process could be suspended, or it could be asleep, and so on and so on and so on. Well, TCP connections can be in different states. So, for example, in the limiting case, um, uh, a connection might not exist. There isn't a connection, or it might be listening. Like a server might be listening. It's uh, it's listening to a particular port for the request of a connection, but it hasn't received one yet. It's receiving it's waiting for a SYN packet from a client, say. Or maybe I've sent you a request for a connection. I've sent a SYN synchronization packet, and what I'm now doing, and what I've got to do before I do anything else, is to wait to get an acknowledgement back from you. Maybe the server has sent a SYN plus ACK packet, and it's waiting for me to send it an acknowledgement. On the other hand, if we're both transferring data to one another, we might have well, the state is called established. It's an established state, and there are quite a few other states: fin wait 1, fin wait 2, close wait, etc., etc., etc. Which I don't think we're going to have much time to look at. But what I'd like you to do, and I mean, I think what I'm going to try doing now is just to share my screen with you after I'm going to set up a command line box, and I'm going to share my screen for a moment. And if it crashes, I'll log back in again in a few minutes, so you can take a couple of minutes break. So I'm sharing. Okay, this is no. I think okay. No, 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 no. So just stop sharing that. Um, Let me just say. So let me go back to my original window. So I'm going to run this command called netstat. No, that's not working. So this is happening in real time, and I've just actually typed this command into a command box, and it's showing some of the connections that my machine has formed with the outside world, and it's showing the status in this fourth column. it's showing the state of the connection. So I've got established connections with um, this IP address. I've got an established connection with this IP address and this IP address and so on. And I'm waiting here. I'm waiting, I think, for a connection to be established. Um, so I'm just gonna stop sharing it. Okay, it's a bit daft. So what I'd like you to do at some point, if you are so motivated, is to run the netstep command. And I've somewhere I've actually given you a URL um, to access the what's called the TCP view software application. It's a simple standalone um, application that will actually reveal a lot of interesting information about your machine. I mean, I haven't the faintest idea who owns this IP address, and this looks as though somebody's connecting statistics on how I'm using my machine, which is a bit worrying. And I've got a connection that's waiting to be closed with IP address 207.123, etc., etc. And no idea what this is. And my machine has actually requested a connection by sending a synchronizer, a SYN segment to this IP address. So um, it's all quite interesting. Well, I'm just gonna. Okay, here it is. No, that's not true. Okay, you can't get it from here. That's the old address. But I've actually put it up on Pharos, I think. So try and download it. If you've got a PC rather than, I don't think there is a Mac version of this. From the, I think his name is uh, Christopher Razonovich, who used to work for Microsoft, but is a genius in terms of writing software that investigates the inner workings of your um, laptop. And I can summarize a lot of what I've been talking about is that a client will actually send a request for a connection to a server. What does it do? Well, it just sends a SYN packet. If it receives a SYN plus ACK packet, then I've got an established connection. And if I want to close the connection because I've used the service, used the server, I send a FIN segment to the server, and I should get an ACK back, enter this state, and so on and so on until the connection's actually closed. And similarly for the client, I've got a sort of simple state diagram for that. Okay, so we've still got a bit of time left, so I don't know if anyone's got any comments. Or questions to ask. And remember, you can. I mean, nobody ever does this, but you can send comments or ask questions by email, and you use my IFG email address, or if you need to, just send an email to kindberg@outlook.com. But it's still a bit more work I want to do today. Okay. So, and my own comment is that I think I've got complete recording of this session, so I'll let you have that. But I'll have to make a YouTube video clip and put it onto Pharos as usual. Okay, so socket network programming, and we're building on our work on TCP and our work on streams. What the focus point of the next half an hour, and I guess the first half an hour of the next session, is on TCP servers and clients. And just to remind you, I've actually put an example of quite a simple TCP server and simple client onto your uh, Pharos, on the Pharos computer science course. So I was going to ask you to do an exercise for me, but I won't. I'm going to have to trust Ahmed and Mohammed and Raghat and Ikram and Razan to actually do this at home. So I want you to run the simple web server and use your browser to connect to the server. And you might say, well, how do I do that? All you have to do is to write in as a URL, is to write something like localhost colon 8080, or I can't remember, it might be 1234. You'll have to look at the program to find out what the port is that I want you to connect. I want you to connect your browser to. Right. You could actually even use the utility program netstat to check that you have got a connection, and forget about this. The next bit, it's not part of my intended practical work. Can use streams and readers to program input and output for TCP servers and TCP clients. And going back to the work that we did on streams, the stream is just an endpoint that supports various methods for doing input and output. And a reader is formed from an input stream. And when you see, and I'm sure I've said this before, when you see a diagram of this form, I'm just saying from, say, an input stream, you can form something like a buffered input stream, and then you might be able to perform a filtered input stream. The point of doing to construct these sorts of entities is that this blue object will offer you appropriate methods for your purposes. Makes life easier, in other words. So, socket programming with TCP. We're using sockets. Right. First of all, logically, a client must contact the server, and the server process logically in turn must be running, and the server itself must have created a socket that will welcome the client's contact. And a client contacts the server by simply creating a client's local TCP socket. In other words, it creates a socket. Somewhere in the client program, you create a socket. And that's really easy to do. How do you do that? Well, you have to specify an IP address and a port number of the remote server. And when the client creates a socket in Java, The client TCP, whether or not you're aware of it, will establish a connection to the server TCP using this three-way handshake. You don't see it. Java makes life very easy for you. So you don't have to worry about that. But that's what happens. When a server is contacted by a client, the server TCP creates a new socket, a unique socket, for the server process to communicate with the client. And the beauty of a server doing this is that it could also create 20 more sockets to cope with communication with 20 other clients other than you. In other words, a TCP server can allow a server to talk with multiple clients at the same time, concurrently. And it's only the source port numbers being used that will distinguish the clients. Okay, TCP, I think we know by now, is going to provide reliable in-order transfer of bytes. In other words, a pipeline or a virtual stream between the client and the server. And if you take a top-level view of what's going on, it's this. So a server is going to run on some host, and you create a socket, and you specify port number. For incoming requests, you create a welcome socket, and you do all that by means of writing something like welcome socket, and that's my name, is equal to, is assigned value of the result of creating a new server socket listening on ports X, and whatever you've decided to do. And the logic of the program is simply this. First of all, you wait for an incoming request. When you get one, you write connection socket is assigned the result of accepting a welcome socket. This is the welcome socket. You're going to accept a connection. So this is a method belonging to welcome socket. Welcome socket is a server socket. It's an instance of server socket. And as soon as you've accepted a request from a client, you can read a request from the connection socket. This is the socket that's been created for the client. And you can talk, you can communicate back to the client using the connection socket. And when you've read a request and you've written a reply, if that's what you want the server to do, you can close the connection with the client. Okay, so on the client side, when you're waiting, the server's going to wait for an incoming request. What happens on the client side is that you create a socket and you use the socket simply to connect to a particular IP address and port number. And you can do that simply by writing something like client socket equals socket. In fact, it's going to be new socket, and in the brackets you're specifying an IP address and a port number. So this is just a bit of a simplification of the code. Once you've done that, you can send a request which is going to be received by the server. Then you can wait to get a reply from the client, from the server. Finished? Are you happy with the result? You can close the connection. So in the example programs I've given you, what the client does is to create a connection with a running server. then it sends a request in the form of just sends a sentence to the server. The server's listening. It's going to read the sentence in. Then it's going to change the sentence into uppercase and send the result back to you. And you've finished. That's it. And diagrammatically, I don't know whether you can see this, is that um, on the left hand side I've got the client, and what the client does is to create a socket, and you specify the IP address of the server, and it's this socket I'm connecting to. It's this IP IP socket, sorry, IP port number I'm connecting to, and all that is done for me in Java. And then the server is actually going to accept a connection. It's going to accept the connection by creating a dedicated socket to talk to me bi-directionally on. So that's the sort of overview of what's happening. And this might sound a bit complicated, but it's okay. So this is a um, blown up diagram, and what the client does is to, by creating a socket with a port number and an IP address, you're going to do a three-way handshake with this server here. And when the server establishes synchronization, it's going to create a connection socket. This is the socket. It's going to create a one-off socket to talk to this client, and it can receive bytes and send bytes to the client. Right, and I've just got a few more minutes left, so let's give you. This is the architecture of a client and my client, and what I'm going to do is to use a stream. It's going to use system.in, that's this basic input stream attached to my keyboard to read in data, and I think we're going to buffer it a little bit so I can read in whole lines from the keyboard, and then I'm going to create this socket, and I can send the line that I've read in out on this stream. Remember, a stream is just a gateway, it's a doorway, and it offers me methods to send data, and after I've sent data I'm just going to wait for a reply from the server on this stream, and this stream is called in from server, and when I receive data I'm going to send it to my screen. Right? So the example client server app, the client will read a line from the standard input and sends it to the server via an out to server stream, which I've obtained from the socket. The server will read the line from the socket, this socket. I've sent it out. Alright. Sorry, I've got this all the way around. This is out to. So this is the connection. Yeah, this is. I'm going to send it out on this stream. That goes to the server. I'm going to wait for the server to convert the line to uppercase, and it will send it back to the client using, and I can receive it using this stream. And the client reads and prints the modified line from the socket. So logically, that seems very straightforward. And I'm breaking that down into 4 steps. And I'm going to read data from the keyboard using this line here. this corresponds to this. This is connected to my keyboard, and I'm using input stream reader attached to the basic system.in stream, which is connected to my keyboard. And what input stream reader allows me to do is to read lines. Okay, to read lines. Or perhaps there's a bit more to be done. I don't know. But we're not quite done yet. We need to join this to a buffered reader. So it's the buffered reader bit. I've got an input stream reader here, but I want to buffer it. Why? Because I want to be able to read whole lines from this stream. How do I do that? Well, again, it looks a bit messy, but this is the Java. I'm going to use I'm going to create an object. That's a buffered reader object. How am I doing that? Well, I'm going to create an input stream reader attached to the system in basic input stream. And these three entities are going to give me this. This is the basic, the red is the basic system.in stream attached to my keyboard. This is an input stream reader. It's going to be able to, it allows me to read bigger chunks rather than numbers or characters, single characters that system.in provides a method to do. And finally, I'm going to create a buffered reader which allows me to read whole lines. Whole lines. Okay, so I've given you a little bit. What's the point of making this new composite? Don't be worried by that diagram. Try and just um, accept the claims I'm making for it. So basic input stream class, system.in is a basic input stream class which is byte oriented, and it has a reader. There's a possibility of creating a reader from it and so on. And we use a buffered reader to read bigger chunks of data, whole lines. So as a simple example, don't worry about that. How do we build a stream to connect to the server? So I'm reading in data from the keyboard. I now want to send it out to the network. I want an output stream. How do I manage all that? It's very similar to the foregoing. And what I'm going to do is to use something called data output stream, which I have mentioned before. And out to server, I'll finish after in a couple of minutes. Out to server is my name for a data output stream object. Okay, and it results from creating a new data output stream, which users is attached to an output stream that I've got from the socket. I've obtained from the socket. Remember, the socket that I've created is going to be called client socket, and it has a method that allows me to identify an output stream associated with that stream. It's a basic stream associated with the socket. This time we use data output stream. The reason we're using data output stream is that it's going to enable us to write bytes. It's going to write bytes, not a single byte. I want to be able to write several bytes at a time to send data. Okay, so you might just need to be reminded about client socket. This is a socket, and I can get the output stream associated with that socket by using this method. This expression is going to return an output stream. I'm going to use that output stream to create a data output stream. out to server results from attaching a data output stream object to an output stream that I've identified from the client's docket. So it looks quite complex, but um, it's not it's not technically too difficult. I mean that's what I'm doing. I think pictorially that's what I'm doing. If I've got an output stream, I can make a data output stream from it. That's what I'm doing. And the output stream here is actually a very simple one, and I'm getting it from Java's socket. I've created a socket to connect to the server, and one thing it allows me to do is to get an input stream which allows me to read data from the server, and an output stream which allows me to communicate with the server. Okay, so I'm, I'm very close to time, but could you, at some point, I need you to. I mean, you've already got plenty to do, I'm sure, but I've given you um, the whole code that I've given you. I think all this code is written up nicely in the Java code I've given you on Pharos. Have a look at it. Just try and understand almost line by line. I've tried to explain it in steps. I've broken up this horrible line here into steps. Can you have a look at that? Just have a look at that. So yeah, I mean, I put all the code together for you, and here's the server. Okay, the server the server is actually listening to port 6789, and just going back a little bit, the client somewhere is creating a socket that connects to um, the name of the server on port 6789. Alright, this is actually going to be an IP address, not a name, an IP address. So will you try it out? Because hopefully you know it should fill you with a sense that, well, you too could write internet servers and clients of any description. I mean, we're looking at the absolute key aspects of writing servers and clients in Java, and it should give you a sense of empowerment. I mean, whether or not you're going to use it ever in the future is neither here nor there, but you could do. You could do. Okay, I'm finished there, and thank you for your patience. As I said, I've put all the materials apart from a copy of the video clip onto Pharos, and I'll do that quite soon. Okay, so thank you for the stalwart students who've remained to the very end, Ahmad, Mohammed and Ragad. And see you next week. Okay, so I'll say goodbye. Take care. If anyone is actually listening. Alright. Goodbye. Ragad, do get in touch with me at some point. try. I mean, are you? You know, if you've got any, if there are any issues, just let me know, will you? If there's one thing I can do to help, let me know. So I'm just going to temporarily resume recording, and then I'm going to leave leave the session. All right. So I'm going to end the meeting now. So goodbye. See you next week. God bless.